Great. Yeah, welcome to my talk on NTP and on our Rust implementation of NTP called NTP-DRS, which we believe takes NTP into the modern era. So, what is NTP? NTP stands for the Network Time Protocol, and it is a protocol for synchronizing time over the network. And in practice with the network, we usually mean the internet, so some sort of big, untrusted network. So why do we need to synchronize time over this network? Like, certainly all of our devices have clocks in them, and they seem to work perfectly fine. But they need to be light, they need to be cheap, they need to be sort of shock resistant, and so they aren't actually the best at keeping a correct time. They will sort of fluctuate, they will drift away from what the true time is, sort of as time goes on. And normally for humans, this doesn't really matter, right? Like if you're late to a meeting by a millisecond, no one will really care. But for computer systems, they are much more sensitive to sort of small differences in time between different machines. And so there's two sort of topics here. One is about consistency, where if we imagine that we have two machines and they communicate with each other on some task, and they send messages back and forth, and at some point we hit an error, we hit a panic, we would like to know what events led up to this panic event. And so the sort of simplest way to do that is to take the logs of the two machines, the timestamped logs of the two machines, and sort of interleave them together into one global timeline. Right? So what we would do is take the two files, concatenate them together, and sort by timestamp. But this only works when the two machines are sort of reasonably synchronized with each other. Otherwise, we can get weird scenarios where like messages are received before they are even sent. And this would, of course, be terrible in terms of debugging. And this is sort of a simple example. There are many more sort of subtle examples of desynchronized machines in a system causing all sorts of subtle errors. The second area is security, because a lot of sort of security mechanisms, especially on the internet, rely on being able to revoke or expire keys at a particular point in time. In particular, HTTPS, which is backed by TLS. And so here I have a practical example. So at Tweede Golf, where I work, we run our own GitLab server. And sort of unbeknownst to us, the NTP daemon, so the program that does the synchronization on that machine, had crashed, and we hadn't noticed because no one knows what NTP is, right? And so one day we went to log in to our GitLab server, and we used two-factor authentication, and it didn't work, right? The key had expired. And so we tried again, and the key was immediately expired again. And so what had happened is that on this server, the clock had drifted so far that any new two-factor authentication key that we would get was already considered expired. So it was valid to the rest of the world, but it was expired on this particular machine because its clock was just way off. Now that is kind of annoying because you need to, like SSH into the machine and reboot a bunch of stuff. But the inverse of this problem is way, way worse, where you can take a certificate that is expired according to the true time and trick a machine into believing that it is still valid by manipulating its clock. And so this is sort of a starting point for further attacks on your system. And these two things combined mean that an attacker could either like really do something nasty with certificates or just cause chaos on your system by causing desynchronization. And so we have to take security of our implementation incredibly seriously. So now that we know that NTP is sort of important, it's a sort of fundamental part of the internet, let's learn a little bit about how it actually works. So if we want to synchronize to true time, someone needs to have the true time. Someone needs to know what time it is right now. And in practice, this is done using atomic clocks at various places around the world. These are these, like incredibly precise clocks that drift by like a nanosecond over the lifespan of the universe. Because they are so precise, they're also very expensive. And so unfortunately, we don't have one of those at the office yet, although given what we do, it might be sort of inevitable that we eventually will. But for the time being, we have a GPS antenna, because GPS satellites and similar satellites also provide a very accurate time signal. And so in practice, what we have to do is chuck this antenna out of the window, because the office turns out to be a Faraday cage for those wavelengths. But once we do that, once we hook up a cable to some random antenna in the street, we can get this very accurate source of true time. Or in any case, it is accurate enough. It's less accurate than an atomic clock, but it's more than good enough for the internet. Like in practice, we can get down to about a millisecond, plus or minus what the actual true time is. After that, the noise in the signal just becomes so much that you can't really do much better than that on a network as sort of chaotic as the internet. So these antennas and these atomic clocks are very good at keeping the time precisely, but they're not that good at serving millions of requests. So we can't have the whole internet talking to this sort of small number of machines. And this is where NTP comes in, to sort of distribute this true time across the network. And so we see these sort of Stratum 2 servers, those are NTP servers that listen to the true time from sort of sources of true time, and then provide that time to further clients. And this sort of cascades down all the way to consumer devices. Then asking someone for, like, hey, what is the time right now, is not as simple as it seems, because by the time that message gets back to you, some time will have passed. There is some in-flight time, some transmission delay. And this transmission delay is significant enough that we need to correct for it. So in practice, what we need to do is actually collect 4 timestamps, 2 for the client and 2 for the server, and this gives enough information to sort of correct for this transmission delay under some assumptions. We also do some further statistics to sort of reduce the effect of noise in this signal. So there's some complicated Kalman filter stuff going on in our implementation. And then finally, we want to always listen to multiple sources of time. If we listen to just one, someone might trip over the power cable there, and we sort of like drift off, which we might not notice, right, until like a month later when your login doesn't work. Or alternatively, an attacker might compromise this one machine, and we in effect follow it blindly, and so they can just manipulate our time in whatever way they want and cause either chaos or actually sort of launch a series of further attacks. So in effect, we have like multiple sources that we listen to. We sort of take the average intuitively and then update the system clock. And there's sort of 2 ways to do this. You can actually set the time. And we do this for big jumps, so after maybe a machine has been sort of in a closet for 6 months. But software doesn't really like it when you mess with the system time. And so that is why, in practice, we usually do phase adjustments. So we speed up or slow down the clock slightly, so that eventually we sort of hone into the true frequency at that moment. So with that, you might wonder, why bother? Why bother with all of this? Certainly there are existing implementations. NTP is it originates in the 1980s. It's been around since sort of the origins of the internet. And so why make a new implementation now? And perhaps specifically, why make one in Rust? And the reasons for this are actually mostly social, in that there are existing implementations, but they are maintained by a very small group of people. So there's like maybe 3 or 4 sort of production-worthy implementations, and they are usually maintained by like 1 person or like 3 or 5. Very small crowds, and these people are getting older. And this knowledge is clearly very sort of vital to having the internet work. And so having more people that know how this infrastructure works is a good thing. Also, these existing implementations are old C code bases, which means that they have a very hard time attracting newcomers and new contributors. And so in effect, when we build a Rust implementation, we hardly looked at these C code bases at all because we just couldn't efficiently find what we were looking for. So we really operated from the original specification, and occasionally did like a grep through those C code bases. Then there are, of course, also technical reasons that we might consider a rewrite or really a new implementation in a modern language. So in particular, that means the tooling is a lot better, the sort of beginner story is a lot better, the documentation is generally a lot better. And so in particular, Rust brings a couple of cool things to the table here. It is, of course, a systems programming language, so that means that it is very efficient. Also, we can guarantee no seg faults. It's not really something you can do for any sort of non-trivial C program. We do have a little bit of unsafe in the code base, which is mostly around interacting with the operating system. So actually adjusting the clock is just inherently sort of uncheckable by the Rust compiler. And we need to do some stuff with UDP ports to have it actually sort of provide timestamps for us, the timestamps that we sort of saw earlier. But like, none of that is very scary stuff. Then, of course, the Rust tooling is very good. It's sort of been mentioned already, how much we like that tooling. And here in particular, fuzzing is really important. When we are an NTP server, we are just, in effect, opening up a UDP port to the internet. And this is sort of a dangerous thing to do, because anything could end up at that UDP port. And so we want to make sure that we don't panic on any weird input, we don't loop forever on any weird input, we don't just use a lot of memory on weird input, and so we just continually fuzz this endpoint with random bytes. And so far that has been really effective both in sort of finding bugs and just gaining confidence in our implementation. And then finally, we have the crates.io and sort of the whole Rust ecosystem. So a lot of these existing implementations first need to spend like a lot of lines on re-implementing like half of the Rust standard library, and then like re-implementing half of, in effect, Tokyo, like a threading abstraction. We get to spend all of our lines on basically just fixing the problem of doing NTP. In practice, we're sort of the same line count as the existing implementations, but that is because half of our lines are tests that just end up getting pretty sort of wordy and take up a lot of lines. So we tried to set this project up, and we've sort of since tried this in various other projects as well, where we have a sort of pure core functionality that we try to make as big as possible. And this is in the case of NTP, where sort of all of the parsing code lives, all of the state machines live, and all of the sort of decision logic for, given these measurements, given these timestamps, what should the clock do? It doesn't actually move the clock forward or backward, it just describes what it should do. And so this pure core is very testable. I didn't actually try it, but I feel like it should just work on Windows even, which is not normally a target we support, but this is just Rust code, and it should run everywhere. And it's easy to test, easy to fuzz. And then, of course, you need to make the rubber hit the road. You need to actually do something in the world, and so that is where we have sort of an effectful shell. The pure core is sort of all sync code, just box standard Rust code. In the effectful shell, we add Tokyo. And so we do, we use async and await for actually doing our effects. And this is also where actually updating the clock happens. It's where we actually send requests out and where we, for instance, like read the configuration file and stuff like that. It makes assumptions about the underlying platform and about the underlying OS. So something that's sort of cool about how we have sort of managed to make this work funding-wise is that we can do a lot of open source work. And so we try to sort of contribute back the things that we have sort of figured out in Rust how to do. So in particular, there's a bunch of like pretty obscure, weird timestamping APIs and related data types that no one had bothered to add to libc for Rust. And so we got to add those. And this is actually a pretty fun process. It's not very hard, and generally you get sort of quick feedback on that. What was much cooler, but also took a lot more time, was integrating support in Tokyo for awaiting error and priority events, which are sort of Linux-specific things. This is sort of cool where they abuse an error reporting mechanism for actually giving you useful information. This seems to happen all over the place. And so it's really neat that now everyone can use that, and also we can use that. We had to do a bunch of unsafe stuff before we got this upstreamed. So we've been going at this project for about 1.5 years now. It originates as an internet security research group project. So they back Russells, they do Let's Encrypt, and they sort of support a bunch of other memory-safe implementations of various sort of foundational building blocks of the internet. After about half a year, we had most of sort of standard NTP covered, and we went on to NTS, which uses TLS encryption to sort of make sure that you're actually receiving the time from the server that you think you are receiving it from. And then, like development continued, fixed a bunch of bugs, and then over the summer we actually got to try this sort of pure core effectful shell idea by adding support for more targets. And so these, the macOS FreeBSD and Muscle, are actually all community contributions, sort of proving that Rust is way easier to sort of contribute to. And macOS is kind of for fun. FreeBSD is cool. We got a bunch of their community to sort of help us set it up. And Muscle is actually very useful for making sort of statically linked binaries. So now we're really close to a 1.0 release, and we also have funding now from the Sovereign Tech Fund to sort of continue development well into 2024, and also do a bunch of like community stuff and experimental things. For instance, working on the next version of the standard. And also we want to make like, NTS sort of easier to use, because it's not actually used very much in practice. And we did spend a bunch of time on it, and we believe that it makes the world a more secure place. So we want to spend some energy there. Then with a 1.0 release, we also want to be in the package repositories. And this turns out to be a bit of a process, because they're built for C code, ultimately. But I believe sudo rs, which is a project that some of my colleagues work on, got in to Debian recently. So I'm sure that NTPDRS will follow soon. And also for Fedora, we are sort of like, the process has been started, it's ongoing, it just takes a little while. But we should get there soon. So if you want to try NTPDRS today, you can. It's now much better, actually, than even like a month ago, because we actually have documentation now, good user documentation. We provide installers on Linux that you can just get. And for other platforms, for FreeBSD, there's actually also sort of an installer through their infrastructure. For other platforms, we provide some instructions. The project is just Rust code, but to have it actually sort of run in the background and not conflict with anything else, you need some sort of system admin stuff set up. So yeah, like we're really close to 1.0, so maybe you should wait like a week, but it's totally ready to try out, and we're really excited about it. So, in summary, NTP, the Network Time Protocol, is a protocol for synchronizing time over the network. It is essential for consistency, making sure that we don't receive messages before they're sent, and also for security. So making sure that we can invalidate or revoke keys and certificates. And NTPDRS is a Rust implementation of NTP that is now fully featured. It's pretty much doing anything that sort of normal people might want. And we're looking for early adopters, users, and feedback. Thank you.
Thank you, Folkert. Please stay for Q&A session. 大家有没有问题？关于 NTP。
So you mentioned that when there's a rather abrupt time change, the change is phased in over time. How big is this phase-in period typically?
You can configure it. I believe that sort of, it really depends on what you want. Whether you want to synchronize quickly, probably anything sort of, certainly more than an hour, you would probably just jump. Maybe even like a minute, you would just jump. It's fine, probably, especially if you do it once at startup. So we actually have different configurations for how big of a change you can do at startup versus further sort of while it's running. While it's running, it's actually probably a sign that something's very wrong. And so we're much stricter then. But at boot, like you might boot a computer that has been sort of turned off for a decade, and you don't want to use like phase adjustments to get back up to speed. I believe it takes like 1,000 years. We did some calculations recently. So at that point, you totally want to jump, and it's fine. Like everything should work out. You just don't want to jump. Sort of every 16 seconds is normally sort of the lowest interval that NTP will sort of update. You don't want to jump every 16 seconds. It's just, I don't know, like something will break eventually, and it's not nice. And the frequency adjustments work perfectly fine for that.
So you have NTPD-RS and sudo-RS, both rewriting very security-sensitive bundles of C code in Rust. What do you think is the next highest priority item that somebody ought to pick up and run with in terms of value of replacing?
That is interesting. I'm also not sure whether I'm like entirely at liberty to say everything that I know about this. There's certainly more. So I know that work is actively being done on name resolution, on DNS. So that seems like a sort of an obvious candidate. Exactly, yes. I mean, it's hard work and it's taking a while, but there's a bunch of money now flowing in that direction. So that's looking really good. We ourselves are also doing PTP that is, like very related, but perhaps less sort of security sensitive. And then there's a couple of other things in the works. So yeah, I don't know. It's like we'll see how it goes. It's also ultimately sort of not up to us. It's sort of very funding based. It depends on what you can get funding for, more than sort of what is perhaps technically most useful. And we're actually very lucky that we got to do something as obscure as NTP, which probably wouldn't have been the first choice if you had just asked a bunch of people.
Okay.
So you had mentioned that testing the core library and being able to do that without having to do anything that's like effectful. When it comes to like actual hardware testing, do you have any sort of like process for that? Do you have any like, I don't know, particularly bad hardware that like drifts a whole bunch that you can test against, or what's that like?
So what we can do is, like we hook up the antenna, right? And then we have a big, like sort of server rack full of goodies. So in particular, we have some Raspberry Pis. And what you can do is basically just turn them off, and then they desynchronize, and then you turn them back on again, and you see what happens. And so we have a bunch of like sort of measuring tools basically to get that data out. And this sort of compares with the like pulse per second value that we would get from the GPS satellites, and then we just see how our implementation behaves. We see how it does versus others. We also just, you can sort of look at the data and see that it is good. If it's very erratic, then something's weird and we need to fix it. If it's pretty smooth, then we know that we're doing something, we're doing a good job. There was one here?
So does this end up being just a drop-in replacement for existing implementations? And what would it take to get this widely used?
So it's drop-in that it sort of supports everything that a normal person might want to do. There are things that are missing. We skip some things from the specification, from the earlier version, because we know they are unsafe. And so if that is something you rely on, that's, up to you. Also, what is different is that we use a different configuration format. We recently wrote like translation guides between the existing implementations and ours, and we learned once again that it was a very good idea that we picked our custom configuration format. The other stuff is absolutely horrible. It uses like invalid IP addresses to signal that something is like a local device. There's all sorts of crazy hacks in there. So it's drop-in in the sense that it needs a little bit of work, but then it should do anything that you would need to do. What we need for general adoption is more users, right? Like we need some actual big companies to just start using this. We've been in talks for ages, but I don't know. Maybe now that we have a 1.0 release and guarantee no backwards incompatible changes, we can finally sort of push them over the hump. And yeah, also the package stuff is sort of essential for this, right? It just makes it much easier to distribute.
Okay. Once again, thank you. Nice to see it.